Okay, we are recording. We are doing 110 acoustics, and we are continuing in Unit 3 on complex sounds. And if we share screen here and look at where we've come in these particular set of notes for Unit 3. To share screen and highlight the notes. I'll make it a little bit bigger. There you go. So, looking at complex sounds and especially noise and speech. And we kind of finished a little bit last week when we addressed the concept of filters. But here we go. Almost all sounds we hear are complex. They are combinations of many different frequencies. Each frequency may have very different amplitudes and phases. They're basically, here's another place to put a star by. They can be periodic or non-periodic. Periodic means you can see a pattern in the wave. You can see some repetition. Even though the wave might look funny, you can see repetition in it. That means it's going to be tonal. If you don't see any repetition or periodicity, you know, the period of a sound, you don't see any repetition, it's called noise. Okay? It will have no tonality. It might be like, okay, no tonality, but has tonality. But those are noises. Okay? So, until now, we've always just discussed pure tones. Another place to put a star by is spectrum of sound waves versus waveforms of sound waves. Two ways to represent sound. So if I highlight that particular picture here, these would be sound waves, and these would be sound waves, the top here. These are sound waves, of course, because you've got time and amplitude. The bottom here, these are spectra, spectrums, okay? They don't have time. You'll have frequency and amplitude here. Here's another spectrum. Oh, on this particular picture here, this is a phase spectrum. Don't worry about that one. Just leave that one alone. Focus on this guy right here. And if we go here, I'll make it larger. That's a spectrum, okay? And this spectrum is showing discrete frequencies at 100 hertz, 200 hertz. And remember, they don't have to look like this. They can look like these, okay? These are continuous spectra. This is discrete spectrum. It has specific frequencies, and in this example, there's more energy in the lows and less in the highs. Over here, we call these continuous spectrums because they've got everything underneath. Okay? You could call this a white noise spectrum because it's got equal energy across all the different frequencies. And when you think about colors, think about colors. Think of a wheel, okay, like a pie, I would say. Think of a pie, and one slice is green, the other one's yellow, the other one's red, the other one's blue, okay? If you spin that wheel, that color wheel, they'll all look white, okay? White is a combination of all the different colors together. They make white. And when you have a spectrum with equal energy across all the different frequencies from low to mids to highs, we call that a white spectrum. And when you think about colors and light, red is the lowest frequency light and ultraviolet is the highest frequency light. And they use colors to describe sound spectra as well, because pink noise has more energy in the lows and less in the highs. White noise has equal energy or equal amplitude across all frequencies. We'll get to that in just a bit later today. Alrighty, share screen. So this spectrum here has all the different frequencies in it too, but it has less amplitude for the low frequencies and more amplitude for the highs. And then we talked about adding frequencies together. You could have this sound plus this one, and look at the spectrum here, and the spectrum, and the spectrum. So on the left, you're looking at sound waves. On the right, you're looking at spectrums, okay? And what do spectrums have an advantage for? They show all the different frequencies easily. So you can see that this sound wave here, look at the bottom. It's hard to tell what frequencies are in there. I can't do it. I'd look at that and go, well, okay, here's the time, and how many cycles am I having in, like I can see one kind of a cycle here and another one here and another one here, but then there's all these other little jiggly jags, okay? It's kind of hard. Well, the spectrum says, nope, there's energy here, 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 and here. Okay, so sound waves have an advantage of showing changes over time. Spectrums have the advantage of showing you what frequencies are in a complex sound wave. So here you go. You got energy at 200 hertz, at 400 hertz, at 600 hertz, at 800 hertz. So now you got a combination of adding all these tones together, and you got that one. Okay. Oddly enough, if you removed one of these frequencies, the fundamental frequency, which, by the way, in a spectrum, the fundamental frequency is the lowest frequency in the spectrum. The other sounds are harmonics. Okay? Remember that. The lowest frequency in a spectrum is the fundamental frequency. The remaining ones are equal multiples of the fundamental. Okay? 200, 400, 600, 800, but remember the difference between a harmonic and an octave. An octave is when you double the frequency. So this harmonic is 1 octave higher than this one, yep, because it's double, okay? But this one here isn't an octave higher, okay? It's just an equal multiple. It's 200 hertz higher. And this one's 200 hertz higher. So if you're looking at octaves, you go here to 400, to 800, to 1600, you know what I mean? You know what I mean? Weirdest thing is when you take away the fundamental frequency, you're still going to basically hear overall like a 200 hertz tone because these multiples are 200 hertz apart. We'll talk more about that after the midterm when we get into psychoacoustics, more like the perception of sound. Last week we also talked about weird sounds that you can add together to make weird looking sound waves. So if you follow certain rules, you're going to get really weird looking sound waves, okay? This is a sawtooth wave because its shape resembles the shape of a saw. And how did they get that? Well, they added this sound and this one according to certain rules. Oh, it had to follow rules like, okay, you had this sound, and then this one had to be a little bit less in amplitude, and this one had to be a little bit less in amplitude. Look at these. They are equal multiples of the fundamental harmonics, but you're adding them together according to this kind of a spectrum. You're following this rule. And when you do that, you're going to get a sawtooth wave if you keep adding the frequencies together. And here, you're adding these frequencies together. And basically, when you add this one to this one, you get this wave. And then you add a third one, you get this wave. And you add a fourth one, and you're starting to the wave's starting to look square. Okay? Little Jack Horner sat in the corner and got a square rear end. Anyway, you know what I mean. So what they did was they took every other harmonic. So look, they took 400 hertz is out. And 800 hertz here is out, and 1200 is out. So they did a similar thing as they did here, but they just took every other one out. And when you did that, you got a square wave. Oh, well, don't think you have to memorize that, because I don't. Okay, I'm just showing you pictures here of how weird sounds can be made. Here's a triangular wave, and it was made by adding, according to this rule, these really dropped in amplitude, and it's every other harmonic. So it's just a way to show you that when you're adding sounds together in certain ways, you can get odd looking waves. So sawtooth wave, square wave, here's its amplitude spectrum. Here's its amplitude spectrum. Notice these guys drop at a certain rate, 6 dB per octave, 6 dB per octave. But this one has every other harmonic is gone. And here it's just showing you more of like a sum total, like everything together. Don't worry about the right-hand ones, I don't care. And, this is just to show you again, spectrums and waves. Oh, look at the bottom one, white noise. See the spectrum? Flat. It's got equal amplitude for all the different frequencies. And look at the top one. I see repetition. I see repetition. Third one, repetition. This one here. All of these top four would be tonal. They would sound tonal in some way. Not the white noise. It's going to be... So here's a way of adding sounds that are really close together on the bottom versus far apart in frequency. And when you add sounds that are really close together in frequency, you tend to get beats. Okay? So if you add a 1000 hertz tone and a 1001 hertz tone, they're going to be completely in phase, and then they're going to be completely out of phase. Remember, the frequencies are very close together. Like the windshield wipers on a bus. Their fall are really close together, but they're a little bit different. So eventually this finger is going to be down before this one. And then this finger is going to be down before that one. And then this one's going to be further along. And then this one. And then this one's going to be way further along. Until finally they're going to be out of phase completely. And after a while they'll be in phase again. So frequencies close together, okay, are going to go wax and wane. Wow, wow, wow. You're going to get beats. Wow, 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 wow. So if you have a 1000 hertz tone and a 1001 hertz tone, you're going to have 1 beat per second. 1000 hertz tone and a 1002 hertz tone, 2 beats per second. The difference between the two frequencies will be the number of beats you hear per second, until finally they're far apart enough that you're going to hear 2 separate tones. So now, sharing screen, and look where we've come in our notes. We'll just look at the notes now. Okay, so we've covered basically spectrum versus sound waves, line versus continuous spectrum, or discrete. Oh, you remember from last week, Monsieur Fourier, the guy who discovered that complex sounds are made of different frequencies. A Fourier analysis is a spectrum. Put a star by that. Fundamental frequency is the lowest frequency in a complex sound. Then we covered triangular, square, and sawtooth waves just for the sheer heck of it. Then we talked about beats. Okay? And then we get to spectrum of 3 complex sounds. And this is an interesting slide too. Here you go. And last week we described 3 different musical instruments. This might be a trumpet, this might be a clarinet, who knows, this might be another kind of instrument. Notice they all have the same fundamental frequency. They don't have to, we're just showing you an example. And the same harmonics, but the harmonics will be of different amplitudes due to the individual mass and stiffness of the horn in question. So let's say you're blowing into a trumpet, and the number of times your lips are vibrating, you know, you're into the trumpet. That's going to be the fundamental frequency. And then the trumpet, due to its mass and its stiffness, is going to resonate at different frequencies. And if this one here, oh, I wish that black bar would go away on the top here. I can't. There you go away. This one likes 900 hertz. It's resonating there. It doesn't like 1500. It kind of likes 2100 hertz. Okay, so it's due to its mass and stiffness, it's going to resonate with certain frequencies. This instrument's different again, and the third one's different again. Okay, and this kind of brings us to speech, because when you're looking at speech, the individual male voice, the fundamental frequency of Bob, Tom, Tim, and Harry, okay, and Ted. Our fundamental frequencies of our vocal folds is going to be around 125 hertz. And a female voice is going to have a fundamental frequency of around 250 hertz. Why do various men sound different from each other? And why do different women have different voices? Because the resonance of the head is different from person to person. So you can think of the larynx or the voice as the reed that's the fundamental frequency, and think of the face as the horn. And everybody's head has different mass and stiffnesses, and it's going to resonate differently. And that's why people's voices sound different. You see, if we're going to learn about hearing aids, the most important sound for a hearing aid is speech. And we've got to learn a little bit about what speech is. All righty, share screen. Back to where we were, because last week we got up to filters. So here the resonance is where the opposition due to mass is equal to the opposition due to stiffness. And we all know that when you're looking at the notes here, spectrum of 3 complex sounds, it's very important to make sure that we understand opposition due to mass. Mass resonates with lows, opposes highs. Stiffness resonates with highs, opposes lows. Those oppositions are called reactants. Okay? And then when you add resistance to it, because every object poses some friction to the passage of sound, and you put those 3 things together, opposition due to mass, opposition due to stiffness, and resistance, you've got impedance. There you go. Okay, and that's the flip side of resonance. A frown is an upside down smile. The impedance, what isn't impeded, resonates. Okay, and the impedances and the resonances act as filters. In speech, they sculpt and shape the basic buzz of the vocal folds or larynx. Filters. They literally filter it, just like a vacuum has a filter. It collects the dust, but it lets the air get through. Okay, it impedes the dust and it lets the air get through. Okay, filters in any sound transmission. They determine what is impeded and what resonates. So here's filters. You can have all kinds of different filters. This is just showing you 4. Okay, this is the low pass filter. It's letting lows pass. It's not letting highs get through. This is a high pass. It's letting highs get through. It's not letting lows get through. This is a band pass. It's letting mid ones get through, but not the lows and the highs. This one's letting nothing get through except this little notch over here. You can have all kinds of filters. Don't worry about this. This is kind of like something from outer space. Okay, so waveform, noise, no pattern, white noise. It might be like a radio between stations. Pink noise. See the difference? Pink has the same energy in the lows, but less in the highs. And when you think about speech, overall in speech, speech has a spectrum a lot like pink noise. Because the vowels, the low frequencies of speech are louder, and the high frequency consonants of speech are softer. So when you think of the name Paul, isn't very loud. It's the ah. Okay? When you think of the word car, what's the loudest part of car? It's the ah. Okay? The k isn't very loud. So when you're thinking of speech, vowels, A, E, I, O, U, are loud and low. Okay? Consonants are soft and high-pitched. So the spectrum of speech is on an angle, just like pink noise. Okay? The vowels are louder, the consonants are softer. The vowels are low-pitched, the consonants are high-pitched. Share screen. Look at our now we'll get out of here. Look at our notes and see where we are. Noise has a non-periodic waveform. It's not tonal. The waveform does not show a pattern of repetition over time. And oh, put a star by this one here. Noise can be turbulent or transient. Okay? Turbulent means it keeps going. Like a waterfall. Okay? Like a radio between stations. Like a fan or an air conditioner. Okay? But noise can also be transient. Like a door slam. It's started and done. Bam. Like a pop. Okay? Turbulent or transient. Turbulent or transient. Don't worry about these three sentences here. Leave them alone. Just leave them. Who cares? In speech, consonants are the noise, and consonants can be turbulent or transient. Think of a turbulent consonant, one you can sustain and continue. That would be like the letter S. S. Letter F. F. A transient one might be like the letter K. K. I can't continue K. K. Once the horse is out of the barn, it's gone. Well, I can repeat. I can go. K, 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 k. That's not fair. I can't continue the letter K. Okay, I can continue the letter S or F. All right, so very important to understand that. Okay, you have turbulent consonants and you have continuous consonants, or turbulent and transient. Okay, waveform and spectrums for different kinds of noise. You can have a broadband noise, and I gave you two examples, white and pink. Why are they called broadband? Because they've got lots of different frequencies in them. They cover a broad range. Look, it's got all kinds of frequencies in it. Even pink does, even though the amplitude gets smaller as the frequencies get higher, doesn't matter. It's still's got everything in it. Okay? So here's white noise, a waveform, and this would be its actual measured spectrum, fairly flat. Here's low-pass noise, or pink noise. And notice its energy is mostly in the lows and goes down in the highs. And here's a band-pass noise. I can't see much repetition in its waveform either, so it's probably noise. And here, it happens to have most energy in these frequencies. Not over here on the left, not in the right. It's a band-pass. Okay, so low pass, everything pass, broadband. This is still broadband. This is getting to be a narrow band. The spectrum of average conversational speech is a lot like pink noise. More energy in the vowels, less energy in the high frequency consonants. And here is a person's vocal folds, or larynx. Air is breathed up from the lungs and goes through, and then out the oral cavity and through the nasal, through the nose as well, okay? And everyone's head is shaped differently. And last week, I believe I blew through two pieces of paper and they stuck together. If you watched the Zoom session last week, I was blowing through two pieces of paper and they stuck together. And the reason they stuck together, here's vocal folds, okay? Showing you going through the horn, the mass and stiffness of someone's head speech. And here's the strings of a guitar. And look, they're resonating the box of the guitar. So that's why a guitar is going to have a unique sound. It's going to be different from a violin, or if you made this shape here different, the guitar would sound different. Even though the strings might be identical, the sound would be different because the mass and stiffness of the box would be different. Same with the vocal folds. They might be quite the same in Tim as in Todd, but Tim's voice is going to sound different from Todd's because Tim's head has different mass and stiffness from Todd's. And when you're looking at vocal folds, this is the general sequence over time. They blow apart, and because wind is blowing through them, it sucks them together, just like the papers that I showed you last week when I blew through them. What did we call that last week? The Bernoulli effect. B-E-R-N-O-U-N, Bernoulli. B-E-R-N-O-U-N-O-U-L-L-I, Bernoulli, okay, effect. So you're blowing air through two things, it's going to suck them together. And then air continues to burst them apart. Air rushing through, sucks them back together again. And then air blowing underneath, bursts them apart. Air blowing through, sucks them together again. You've got that repetition, and in a male that happens 125 times per second, and in a female that happens about 250 hertz times per second. And in a baby it happens about 500 times a second. Okay, so that is what makes the fundamental frequency of a voice, is how many times per second your vocal folds are slamming together. So never think that you have vocal cords, because you don't. You don't have strings going across something like a guitar. They're folds. They're connected at one end, and they close or open. Close or open. So when air rushes through, it sucks them together. Air built up underneath, poof, bursts it apart. Air rushing through sucks them together. Air underneath, poof, bursts it apart. In a male, 125 times a second. That's the fundamental frequency of a male voice. Female voice, 250 times per second. Wild. Speech is a wild thing. All right. Narrow band noise. It's smaller widths, smaller bands that are clustered around a center frequency. And when we do hearing tests, I'll stop sharing for a second. We use narrowband and broadband noise. When you're doing a hearing test, you're putting a tone in the ear, and the guy raises a hand whenever he hears the tone. And the tone is made softer and softer until the person can't hear it anymore. But what if this ear is really bad and this ear is really good? If I put a lot of sound into a bad ear, it might cross my skull and get to my good ear. And I'm going to raise my hand. So if that's the case, if you've got two ears very different from each other, and you've got to put a lot of sound into the bad ear, you want to make sure that the sound doesn't cross the skull and get to the good ear. That's where we use narrowband noise and pink noise. If we're putting 1,000 hertz into the bad ear, we're going to use a narrow band of noise surrounding 1,000 hertz. We're going to put that into the good ear to keep it busy. And we're going to say to the guy, hey, you're going to hear a windy noise in your good ear. Don't mind that. That's just to keep the ear busy. Just raise your hand when you hear the tone in this ear, okay? That's called masking. We put masking noise into a good ear to keep it from participating in the test. And we do that when there's a big difference between the ears, because we want to prevent sound crossing the skull getting to the good ear. So when we are putting speech into the bad ear, we use pink noise, because the spectrum of pink noise is a lot like the spectrum of speech. And when we put 1,000 hertz into the bad ear, we use a narrow band of noise that surrounds 1,000 hertz. When we put 2,000 hertz into the bad ear, we use a narrow band of noise surrounding 2,000 hertz. When we put 4,000 hertz into the bad ear, we use a narrow band of noise surrounding 4,000 hertz. The audiometer automatically does that. You don't have to choose that. It automatically does it, but it's just, that's what you're learning here. So, good. Share screen. Where's the notes? Over here. We often use, don't worry about that, third octave bands, blah, blah, blah. Okay. Speech as a complex sound. Speech as a complex sound. Oh yeah, back up to here. You often hear this one. Third octave bands. That's just the width of the band. Okay, when you're thinking of the band of noise, remember the shot I showed you here? There. It would be about 1/3 of an octave wide. Just a narrow band of noise, wide band, wide band. Okay, that's all that is. Okay, back to speech here. Speech as a complex sound. We went over this. And the word formants, this word right here, formants, those are resonances of the face, resonances of your head, resonances of your vocal tract. Now, your vocal tract is from your throat to your lips. That's your vocal tract, okay? And it, too, is like a cylinder closed at one end, like my cup. Closed at one end, open at the other end, okay? Because the closed end is here, and the open end is here. And your ear canal is one of those too. It's open at one end, and it's closed at the eardrum. See, so you have 2 quarter wave resonators when we talk about speech and hearing. So let's look at that in the notes. Resonance of the vocal tract. Your vocal tract is about 17 centimeters long. Do you recall how long the ear canal is? About 2.5 centimeters long. And always remember what a centimeter is. About the width of your fingernail. Okay? So, we'll move on down here. Voice quality. Trying to find where I can slide down. There you go. This is a very, very important table to look at. Okay? In your notes, you can add to this. Okay? Vowels are periodic. A, E, A, U. Okay? They're tonal. They're low frequency. And I would write underneath low frequency, they are loud. Relatively loud. Unvoiced consonants, f, s, p, t, ch, k. We're not using the voice. And then really internalize this. Put your hand to your throat and say K. K. You didn't feel it vibrate. Say P. You didn't feel it vibrate. Say S. It didn't vibrate. Okay? T. T, t. It didn't vibrate. But, and now say A, U, E, okay? It vibrates. But look at combinations. What if I take the letter F, and I put a voice in it? V, v. Now I got a V. What if I take S, 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 and put a voice in it? Z, Z. Now I have a Z. What if I take and put a voice in it? B, B. Now I have a B. What if I take t, t, and I put a voice in it? D, D. Now I have a D. And that's kind of what the middle column is telling us. When you look at the middle column, the voiced consonant, it's in the middle. It's a combination of noise and tonality. It's got both. And so that's why I put them together like that. F, V, S, Z, P, B, T, D. Look at ch, ch, j, j. Okay? Church or church? Judge. K, 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 g, g. You see, what's really interesting, this is like a little bit of speech pathology, speech therapy. There are 3 places that you can squeeze in your face. Your lips. The second one is your tongue behind your front teeth. And the third one is the back of your tongue against the roof of your mouth. Pataka. Front, middle, back. Front, middle, back. Pataka. That's like patty cake. Patty cake, baker's man, which is why it's a good rhyme for children to learn how to talk. Okay? Pataka. They call that in speech pathology diodocokinesis or something. It has some weird, I'm not a speech pathologist, but at any rate, those are the basic places that we can squeeze together to make sounds of speech. So let's look at our table again here. That's with the lips, front. That's with the tongue against the back of your front teeth. Front again. Again, tongue back against the teeth. Again, the tongue sort of near the back of the front teeth. That's the back, for sure. Okay? Anyway, unvoiced consonants, not using the larynx. Voiced consonants, using the larynx. Vowels, only using the larynx. Okay? Your vocal tract, it says at the bottom here, is a quarter wave resonator. Your vocal tract is a quarter wave resonator. It's going to vibrate with sound waves that are 4 times its length. Always remember that. This is quiz material, okay? Quarter wave resonators are open at one end, closed at the other end. And what do quarter wave resonators do? They resonate with sound waves 4 times their length. So if your vocal tract is 17 centimeters long, it's going to resonate with sound waves that are 17 times 4 centimeters long. And if you do the math, it's going to be about 68 centimeters right here. And the speed of sound in air is 340 meters per second. So 340 meters per second. Now hang on, meters and centimeters, you can't divide apples by oranges. You can only divide apples by apples, okay? So you've got to change centimeters into meters. And 68 centimeters is 0.68 meters. So now you can divide the speed of sound, meters per second, divided by 0.68, 500 hertz. Okay, so that's going to be the resonating frequency of your vocal tract. You sent most people's. It's going to vary from Paul to Saul to Tall to whom all, okay, but essentially, quarter wave resonator. Now, why does your voice get higher when you breathe helium? And have you ever breathed out of a helium balloon? I have. It's hilarious. You breathe out of a helium balloon and your voice is, it's really high pitched. You know why that's the case? Because helium is less dense than air. That's why helium balloons float. Okay? The molecules of helium are further apart. They're not as clustered together as they are in air. And remember what you've learned before. The more dense an object is, the slower sound goes through it. So sound goes faster through helium. But the length of my vocal tract didn't change. So sound goes through helium over 900 meters per second. And when you do 900 meters per second divided by 0.68, you end up with a way higher frequency. And that is why helium makes your voice higher. Okay? Just FYI, you don't need to memorize the numbers, but just get the basic idea. Okay? So here's the math for you. Okay? Wavelength equals speed of sound over frequency. Frequency equals speed of sound over wavelength. Always remember those. It's very simple. The speed of sound is always on the top. Frequency is speed of sound over wavelength. Wavelength is speed of sound over frequency. That's the trick to remember those two. It's just like saying 5 is equal to 10 over 2 and 2 is equal to 10 over 5. Okay, same crap. Okay, good. Speech on a spectrum then, vowels are more intense and they are lower in frequency. Consonants are higher in frequency and they are softer. Vowels carry the energy of speech. There's only 5 to 6 vowels in English. And every word has a vowel. Okay? So vowels don't tell you very much what the word is. Vowels tell you that someone is talking. And I really want to emphasize this because this is the situation of hearing impairment. The hearing impaired, they can hear the vowels quite well because the vowels are louder. And usually hearing loss is more in the treble frequencies. So the hearing impaired client usually has better hearing in the low frequencies and worse hearing in the high frequencies. Trouble hearing treble. And when you've got trouble with treble, you kind of hear the high frequencies now, okay? And when you kind of hear the high frequencies, you have trouble hearing what the word was. Dishes or fishes, kittens or mittens, fat, hat, cat, sat. You have trouble hearing what the person said. And that is why the elderly complain bitterly about young people mumbling, okay? Because they can't hear what the person says. And don't start yelling because when you talk louder, you've just increased the vowels. And they can hear the vowels pretty well. They usually have better hearing in the low frequencies than in the highs. That's where age hits. Age hits the high frequencies. So when you yell, all you're doing is making sounds uncomfortable because they can hear that perfectly well. And by the way, hearing loss usually has the same ceiling of loudness tolerance as normal hearing does. 100 decibels sounds just as loud to a hearing impaired person as it does to someone with normal hearing. Now that's going to be only if the hearing loss is sensory neural. That's going to be only if the hearing loss is due not to middle ear pathology. If you've got earwax or middle ear pathology, you're going to have what they call a conductive hearing loss, a plug in the ear. If you've got a plug in the ear, yeah, you got to talk louder for the person to hear. But 95% of hearing loss doesn't have that. It's hair cell damage in the inner ear. And to them, 100 dB is going to sound like loud, just like it does to someone with normal hearing. Hearing loss just means you can't hear the soft sounds. So the dynamic range between the floor to ceiling has shrunk. It used to be down here, and now it's here. Okay? So when you're yelling, you're making the sound really loud anyway. The guy doesn't like that. You want to just emphasize the high frequencies. And that's exactly what is done with a hearing aid. Hearing aids today amplify high frequencies mostly. Here's how an elderly person hears. An elderly person hears like this. Okay? You can hear my voice, but it's kind of muffled. You can't hear the consonants as well. You can't hear the high frequencies. Always remember, the purpose of a hearing aid is to take that sound and turn it upside down, okay, to increase the high frequencies. And that's exactly what most hearing aids are doing. They are treble emphasis amplifiers, trying desperately to amplify the high frequencies of speech for high frequency hearing loss. So, presbycusis, the most common hearing loss in the world. Sounds like Presbyterian, okay? Church of the Elders. Presbyopia, remember, hits you when you're 40. You can't see close up. You need reading glasses, which is why I have reading glasses. I can see far away, no problem. I just can't see close up. That hits you when you're 40. Presbycusis, hearing loss in the elders. Presby just is Greek for elders. Okay? Presbyterian, Church of the Elders. Presbyopia, vision of the elders. Presbycusis, hearing of the elders. And that's treble hearing loss. So, consonants. They are a mixture of tonality and turbulent or transient noise. Unvoiced consonants are mostly noise with less tonality. Consonants tell the meaning of the word, what someone is saying. Let's just see where we have here. Okay. So remember here. Let's make sure we know what these are. F. Is it turbulent or transient? Can you continue it? Turbulent. Is it turbulent or transient? Can you continue it? Yep. P. Is it turbulent or transient? It's transient. The horse is out of the barn. Transient. Transient. But sh, which isn't on here, okay, could be, but it isn't. It's turbulent. Transient. Anyway, they can be turbulent or transient. Unvoiced ones especially are mostly noise. Voiced ones are combinations. Presbycusis and the audibility of speech. High frequency hearing loss in the elderly population, extremely common. In acoustics of speech, the vowels are loudest. The vowels are normally heard louder than the consonants. With presbycusis, the audibility of the consonants is compromised even more. So what I mean by even more, consonants are softer than vowels at the best of times. They're like pink noise, right? More energy in the lows and less in the highs. Well, when you add hearing loss to it, now you've really diminished the audibility of the high frequency consonants, right? Remember that. Let's look at the picture and finish this talk today, because we can. See where we got though. Where are we going? Oh yeah, here we go. And I'll show you that picture here just a second. Let's look at pink noise here. Spectrum of average conversational speech. Consonants, unvoiced consonants would be here. Vowels would be here. Voiced consonants, the combination would be about in the middle. Okay? Pink noise. Speech spectrum. Note the similarities. So because these are so soft, nature or the creator, whichever is your belief, has made the outer ear have its shape. Because the outer ear is a quarter resonator. And it's going to resonate with sound waves 4 times its length. So if it's 1 inch long, it's going to resonate with sound waves that are 4 inches long. And what's the speed of sound in air? 340 or 343 meters per second. And how many feet per second? 1,130 feet per second. And this is going to resonate with sound waves 4 inches long. Well, you can't divide feet by inches. You've got to divide feet by feet. So what's 3 inches or 4 inches? It's 1/3 of a foot, right? 3 times 4 is 12. So 0.3 feet. Take 1,130 and divide it by 0.3. I'll do it here on my calculator. 1,130 divided by 0.3 equals about 3,766 hertz. So your ear canal is going to resonate with sounds that are about that many hertz. 3,500 hertz, something like that. And if we do meters per second and do it metrically, okay? So the ear canal is 2.5 centimeters long. It's going to resonate with sound waves that are 2.5 times 4. What's 4 times 2.5? 10. So what's 10 centimeters? 0.1 meter. 343 meters per second divided by 0.1 meters is going to equal 3,430 hertz. So either way, when you work it out metrically or imperially, you're going to end up with similar things. So the ear canal, remember, however, and I'll stop, let me just go to the notes here and follow this very carefully. Last thing, resonance of your outer ear canal or external auditory meatus. It too is a cylinder closed at one end, open at the other. So it's also a quarter wave resonator. It's 2.5 centimeters long. 4 times 2.5 is 10 centimeters. 10 centimeters equals 0.1 meter. So wavelength equals speed of sound over frequency. We know the wavelength. Let's find out the frequency. 340 divided by 0.1 is 3,400 hertz. So the resonating frequency of the outer ear would be 3,400 hertz. But the ear canal, excuse me, ear canal is made of flesh and bone. So this resonance is spread out. So now we can close today. Here's the resonance of the outer ear canal. It's spread out. And where are the high frequency consonants? Right here. So this that I'm circling here is made to address this. The fact that the high frequency consonants are naturally softer, the fact that the high frequency consonants are very necessary to tell you what someone said, but they're like gentle china teacups. They're fragile. They're very soft at the best of times. And that's why your outer ear canal has its length. And that's why the concha bowl adds to things too. So when you're looking at this resonance here, this is a simplified this. The ear canal resonance is going to be around here, around 3,500 hertz. See where my cursor is? Okay, if this is 2,000, and that's 5,000, it's going to be around 3,500 hertz. And then your concha bowl, number 3, resonates with around 5,000 to 6,000 hertz. And you add these things together, and you get your T for total. So when you follow the T for total line, that's a lot like the one I drew here. And look what it's giving you. It's giving you about 20 decibels. It's resonating. It's naturally... it's like a wine glass at Christmas. The mass, because it's a quarter wave resonator, it's naturally resonating with high frequencies between about 1,500 hertz and 4,000 hertz. Let's look at the picture so we can really see that. Between about 1,500 hertz, make it larger now, and 4,000 hertz with a peak resonance around 27. And you're giving that added decibels to those soft, high-frequency consonants that are so hard to hear. Here's the letters on an audiogram. An audiogram is the test upon which your hearing results are placed. The right ear would be the circles, O's, and the left ear is X's. And here's the sound of speech. All the letters of speech are superimposed here on the 7 octaves upon which we test hearing. 125, 250, 500, 1,000, 2,000, 4,000, 8,000, 7 octave frequencies. Here's the decibels going down. Okay, so less here, 120 over here. Z, V, Z, V, J, M, D, B. All these are voiced consonants, and then your vowels, A, U, U. Okay, anything that uses the larynx, anything that when you put your hand to your throat vibrates when you make any of these sounds that I'm circling. But what happens here? P, G, Ch, Sh, K, S. Okay, you're getting progressively softer. And that's why you have the resonance of your outer ear canal. It's to give these that extra lift, to make these soft sounds a little bit louder so the person can hear them. Now, the trouble is with treble. Look at this person here. The O's are his right ear, the X's are his left ear. So he can hear the low pitches at around 10 to 15 to 20 decibels. What's normal hearing? 25 decibels or less. So the person has normal hearing for the bass frequencies. He can hear all these sounds, no problem. He just can't hear these sounds. Even though they are amplified by this resonance, that's not enough. The person can't hear them. Okay, so you and I benefit from this outer ear canal resonance because these sounds are very soft. But the person with hearing loss has trouble hearing treble now added to that. So that person cannot hear these. That's why he's saying young people mumble these days. That's the end of the show, folks. I stopped sharing here. We're done Unit 3. So you can really see that we covered speech big time. It's the most important, complex sound for us humans to hear. Sure, the roar of a lion is kind of cool, and the clap of thunder is a complex sound. Those are all noises too. But always remember, speech, its unique properties of tonality and bursts of noise. Tonality with turbulent noise, tonality with transient noise, pure transient noise, pure turbulent, unvoiced. Part turbulent and part tonality, or part transient, part tonality, voiced consonants. And then vowels. Vowels, voiced consonants, unvoiced consonants. Vowels, loud, low, tonal, periodic. Unvoiced consonants, pure noise, either turbulent or transient. Voiced consonants in the center. The spectrum of speech dropping about 6 dB per octave overall. Long-term average speech spectrum. LTAS, LTASS. All that just means is unaided, everyday, average conversational speech. If you took a spectrum of it, you'd find out it dropped mainly in the high frequencies. Elderly have trouble hearing the highs, so they have difficulty hearing what you said. Always remember, vowels are cheap. You got 5 of them. You have thousands of words. Thousands of words have to share 5 or 6 vowels. So vowels tell you diddly squat about what the word is. Vowels just tell you that a word is spoken. It's the all-important consonants that define what the word was. All right. Adios. I'm done. I'm out of here. For those of you doing 120, I'll be back in an hour. We're going to look more at the anatomy of the inner ear. All right, but for now, I'm going to grab a coffee and stop recording.